This lesson we have today is on related rates. So let's first explain what that means, and we're going to use this diagram of ripples in a pond to explain what I mean. So you know what a rate is. It's a rate of change, right? Something per something, miles per hour, feet per second. Those are rates of change. Well, there's lots of things changing in this diagram every second. So the relationship between everything changing is time, okay, every second. Think about it. So these are called concentric circles. You drop a pebble in the pond, and then these concentric circles start emanating out from the center. They all share the same center, and what's increasing every second is the radius of these, right? The radius keeps growing every second. But not only is the radius growing per second, but think about this. The circumference of each of these outer circles, the outer circle keeps expanding and getting larger and larger every second. So the circumference is growing per second. Also the area, all the region in here, the disturbed water, that area, every second that goes by, that disturbed water keeps getting bigger and bigger and bigger. So all these things changing are related with respect to time. What we can do now is use the concept of implicit differentiation, and instead of taking the derivative of everything with respect to x, we're going to take the derivative of everything with respect to time, because that's the underlying commonality. Let's take a look at this problem now. We have a pebble is dropped into a calm pond, and it causes ripples in the form of concentric circles, as we mentioned. That's just blank because it mentions what figure number it is, but I got rid of it. It doesn't apply to our video. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. That makes sense what we just said, right? The radius keeps getting bigger and bigger as time goes by. They're asking when the radius is 4 feet, at what rate is the total area of the disturbed water changing? All right, so at some point, we're going to have a concentric circle here. Our outer circle, let's pretend that's a real circle, and there's our center. There's going to be a moment in time where that radius is 4 feet. And even though the radius is changing at a constant rate of 1 foot per second, 1 foot, 2 feet every second, that doesn't mean that the area is changing at the same rate. It's changing at different rates. In fact, every second that goes by here, it's changing a little bit, but believe it or not, every time a circle gets bigger, that increase in area is huge per second, okay? So it gets bigger, it's a larger number as time goes by. So here's how we solve it. First thing I like to do is identify some information they've given us here. Now notice right here, the radius of the outer ripple is increasing at a constant rate of 1 foot per second. You see the word rate of? That's a derivative. It's a rate of change. But what is it a rate of change of? What is it a change in what over a change in what? Well, it's the change in the radius. Well, look at these. It's foot per second. So the radius is given in feet. And, well, time frame is given in seconds. So this rate of change is radius feet per second, right? The foot per radius over seconds. That equals 1, I'll write feet per second. Just to keep the unit, the radius is in feet, the time is in seconds. And it's a positive 1 because it's increasing. If a change is getting bigger, it's positive, all right? And if it's negative, it's getting smaller. So you may want to write that down in your notes, okay? So negative change decreasing, and positive change, your derivative is increasing. That slope is increasing. Okay. What else do we know here? So what are we asked to find? Let's see what they're asking us to find. It says when the radius is 4 feet, so at some moment in time, what is the rate? We're trying to find a derivative of the area. We want to find the change in the area over time. All right, well then what they're asking us is this in blue. We want to find the change in area over the change in time. At the moment, the radius is 4 feet. And they specify 4 feet because, again, like we said, that radius, it's different. The area is changing at different intervals. We want to know at the moment it's 4 feet. What's the change in the area? We are asked to find the change in the area of a circle. So if we start with the area of a circle, we will take the derivative and be able to get the change in the area of a circle. Everything is with respect to time, so if I take the derivative of a, that becomes 1 dA dt. Every letter is with respect to time, so let's do it implicitly like this. Now remember, pi is just a constant, so it's just 2 times pi, which is 2 pi, and then you reduce the exponent by 1. You took the derivative of an r term with respect to time. We include a dr dt. And there, we'll get into this later, but there is a reason why the derivative of the area is the circumference formula. Think about it. Okay, you don't need to know that for this problem though, but it is something to think about. Let's plug in what we know. We're asked to find the change in the area over time. That's what we want to find, but we want to find it at the moment the radius is 4 feet. All right, so we're going to evaluate it when r is 4. If you're not sure, that little single tick mark is foot. 2 tick marks means inches. Let's continue. So you have a 2, which is a number, a pi, which is a number. The radius, well, we know the radius is 4. And the dr dt, well, how do we find, oh, look at that. That was given to us. They're telling us the change in the radius over time was constant at 1. So at 4 seconds, it was also 1. It's a positive 1. Remember, that's important. If it was decreasing, that would be a negative 1, which obviously changes the answer. You do your math here, and what are you going to get there? 8 pi. Always feel free to leave your answer in terms of pi, unless they ask you to round it to a decimal place, of course. Now, what is our units here? Well, look at the change. Look at the rate, the derivative here. We found area over time. Well, the area, if it's feet, well, area is a squared unit, so it becomes feet squared. And the time frame was given in seconds, so our proper units are feet squared per second. There is your answer. Sometimes I find having steps to follow make these problems a little bit easier to do. So if you do, maybe pause this and get these in your notes, but I'm going to talk these through. Some guidelines when you're doing these related rate problems. You need to identify all the given quantities and what you need to solve for. Okay, so identify what's given to you and what you need to find. And then I do a lot of times I'll do a sketch. I mean, I provided a sketch for the first example. And label quantities. I will be a little bit more detailed on this next example. The first one was just to introduce the concept. All right, so number 2 says write an equation involving the variables whose rates of change are either given or are to be determined. So like we said before, if you need to find the change in the area of a circle, well then you start with the area of a circle. Okay, if you need to find the change in the radius of a circle, well the r is in there as well. You can use that formula so long as they're giving you some information about the area. While I simplified this in my discussion about the topic, this is what I was doing. I was doing the chain rule with implicit differentiation, and we're doing it with respect to time. At that point, then we substitute in what was given to us, and we solve for what we're trying to figure out. All right? There are some steps. If you need a pause, well, pause the video and get them in your notes. I'm going to continue. In our next example, we have a rectangle and we have sides of 6 by, it's a 6 by 2, and it says the sides are changing. It says the length is decreasing. So here we are. The length is decreasing by 9 inches per second. That's a rate of change. We'll identify it in a minute. And the width is shrinking at 5 inches per second. That's a derivative. It's a rate of change. We'll identify it in a moment. What is the rate of change of the area? Okay, well, we are asked to find the change in the area of a rectangle. So why don't we start with the change, the area of a rectangle formula. And I like this diagram just because it kind of visualizes what we need to do here. Let's just pretend this is our outer rectangle right here, right? And that is a 6 by 2, right? We have a 6 by 2. And what's happening is it's decreasing. This thing is getting smaller and smaller as time goes by. We have a 6 by 2 rectangle, and we want to know at that moment in time, a 6 by 2, what is the change in the area of it? Let's see what's given to us. I notice here a rate of change. I see 9 inches per second. You see a rate of change, a ratio, that's a derivative. Well, it's a derivative of the x value. Well, it's the length. Here's the length of a rectangle, and here's the width. There are 2 variables. I'm going to call this x and y. I'm going to call the length x because it's horizontal, and I'm going to call the width y because it's vertical. You can use L and W. I'm going to use x and y. So if the length is x, that means that this would be the change in x over time. And the change in x over time is a negative 9 inches per second. Okay, remember what we said, if it's decreasing, that's a negative rate of change. It's negative. The width, well, if I'm going to call the width y, that means that the change in y would be, well, again, it's shrinking, so it's decreasing. It's getting smaller and smaller, so it's negative 5 inches per second. Those are the two derivatives they gave us. If you chose to keep that as an L and a W, it would just be dL over dt and dW over dt. Let's continue. We must find the change in the area of a rectangle. So let's take the derivative of the area of a rectangle. And since I'm going to call the length width xy, that is the area of our rectangle here. You take the derivative of a with respect to time, that becomes 1 dA dt. Now over here, this is a product rule, okay? We have two variables. You must use the product rule. Watch this. The derivative of x is 1. Leave the second. I took the derivative of the x term, not the y term, so I put a dx dt. Plus, wait a second, plus. Now we leave the x term, which is the first one, and we take the derivative of y, which becomes 1. We took the derivative of the y term. We need a dy dt. Let's see what we got. We want to find the change in the area over time, and we want to evaluate it the moment our x value is 6 and the y value is 2. Right? That was the where we started. Well, if you plug in, we don't need the 1 here, so the y value is 2, and the dx dt, well, the dx dt was given to us up here. This one up here, that's negative 9, so a negative 9 goes there. Plus the x value is 6, we don't need the 1 there, and the dy dt, what's the dy dt? That was given to us, that's negative 5. This right here is negative 18, we got negative 30, that gives you a change, a negative 48. What's the unit? Well, again, look at this, we have a over t. Well, let's go back to our problem. Since the first unit was inches, the area would be inches squared. And time frame is given in seconds, so the proper unit is inches squared per second. What are they asking here? We have air being pumped into a spherical balloon. Okay, so we're assuming our balloon is a sphere. And it's going in at a rate of 4.5 cubic feet per minute. Stop right there. Let's see what they gave us. They're giving us something. They're giving us 4.5, this is a rate of, so that's a derivative, 4.5 cubic feet per minute. And think of it, the air is being pumped in, so the balloon is going to look like this, and then it's going to look like this. It's getting bigger and bigger, so that is a positive rate of change. It's a positive 4.5. And it's in cubic feet per minute. Do you know what that's the rate of change of? If you can't identify it, look at the, let's look at the units they gave us. They gave us a cubic foot, and they gave us minute. Well, the minute is time, and what's the change in the numerator? Well, feet cubed, that's a cubic measurement. That's three-dimensional. That's a volume. Okay, a sphere has volume, so it's the change in the volume over time. If you can't identify it, look at the units. Sometimes the units will give it away. If we're asked to find the change in the volume, let's start with the volume of a sphere. This one is 4/3 pi r cubed. Some we'll give you the volume formula for a sphere, for a cone, some of the harder ones, but we won't give you the volume of a prism, we won't give you the area of a circle. Those we expect you to know from earlier years. All right, let's continue here. So if we're going to take the derivative of this, the derivative of v becomes 1 dv dt. Okay, well, this whole thing is just a coefficient, right? So we're going to do this. We're going to multiply that, which gives us 4 pi. We leave the variable, we reduce the exponent by 1, we took the derivative of an r term, we include dr dt. Now instead of asking us to find the change in the volume, they're giving us the change in the volume. Find the rate of change of the radius when the radius is 2 feet. I didn't finish what we were trying to find here. They're asking us to find the change in the radius. We want to find dr dt, and we want to find it at the moment r equals 2. Okay, now that I've specified that, we can continue. We know dv dt. That is a positive 4.5. That was given to us. This is a 4. This is a pi and the radius. Well, the radius is 2. And the dr dt, that is the only thing we don't know. That's what they're asking us to solve for. Let's do it. 4.5, this is 4, so that's going to be 16 pi dr dt. And if you want to get rid of the 16 pi, you can multiply it by its reciprocal, because that will get that rid of, and that is the same thing over here. And we're going to get yourselves dr dt, the change in the radius over time, is 4.5 over 16 pi. And what are the units? Well, the radius was given to us in feet. That is just a linear measurement for the radius, feet. And that is per second. I'm sorry, per minute. Feet per minute. And it's positive. It's increasing. Well, they gave us the 4.5, and when we plug it in, we're going to get a mathematically correct answer. I want to make sure you realize that when you have a decimal inside of a fraction, that's also a complex fraction. You can't leave it like that. That has to be simplified, okay? Complex fractions must be simplified. Why is that a complex fraction? Well, what is 4.5, right? 4.5. Well, that's 9 halves, right? So this is really 9 halves over 16 pi. It's a complex fraction. How do you get rid of complex fractions? Well, I'm going to do it this way. I notice that I have two denominators. I have a 1 and a 2. What is the common denominator? 2. I'm going to multiply the top and bottom by 2. You've seen me do this in class. Now you can't, there's nothing to cancel out, so you just have 32 pi. So the units don't change. It's still feet per minute. Okay. So this is accepted. All right, our next one, the area of a circle. Pretend it's a circle. There's a center. And it says the area, all right, the change in the area is increasing. It's positive at a constant rate of 124 square meters per minute. That is a rate of change. It's a change in the area. Okay, so that's dA dt. At the instant, the area, so we have a moment where the area is going to equal 100 pi. Okay, at that moment in time, what is the rate of change of the radius? They're asking us to find dr dt at the moment a, or the area, equals 100 pi. Here it says round your answers to 3 decimal places. Fine, let's do what it says. Well, if we're asked to find the change in the area, why don't we start with the area of a circle? Pi r squared. Now we did this one earlier, so this should make sense here. We got dA dt, and then we ended up with 2 pi r dr dt. I'm sorry, 2 pi. But now, rather than asking us for the area, they're asking us for the change in the radius. All right, well, they're giving us dA dt. Over here, dA dt was a positive 124. 2 is a number. Pi is a number. They're saying, now wait a minute, we don't know the radius, but now they're asking us to find dr dt. That makes sense that that's a variable, but we don't know r. Look at what they gave us. They only gave us the area equals 100 pi. How do we figure out what the radius is? Well, let's do it this way. Sometimes you have to do a little extra work. We know that the area of a circle is pi r squared. They're giving us yet we have to work with what they give you. They're giving you the area, not the radius. They're telling you the area is 100 pi, but if you know this formula, guess what you can find? Okay, so I'm going to divide both sides by pi. And that's going to give us 100 squared equals 100, and the radius can't be negative, so it's 10. That's how you're going to find the radius. Sometimes you have to do additional work to find your variable. Now, if we continue in this problem, this is going to be 124 equals 20 pi times dr dt, and we want to solve for dr dt, and that comes out to be 124 over 20 pi. Now this will reduce to, what is that? That's 31 over 5 pi. All right. The only thing is, this one is asking us, it's specifying to round it to 3 decimals. So if it tells you to do that, well then just plug in 31 over 5 pi into your calculator. Don't forget to put 5 pi in parentheses, because if you don't, the calculator is going to do this. 31 divided by 5 times pi. And that's not what you want. You want the pi right there, so put it in parentheses. And rounded to 3 decimal places, you are going to get 1.974. What are the units? Well, it's a change in a radius over the change in time. Now, if the area was given to us in square meters, right, that was a square meters up there, well, that means the radius was just it's a linear measurement, it's meters. And the time frame, well, that's meters per minute.